Well, hey everyone, let's jump right into this explainer and start uncovering the hidden mechanics of the physical world. I mean, have you ever stopped to wonder what's actually happening in the air around you right at this very second? It looks still, right? But today, we're going to look way past that illusion of empty space. We are taking a journey straight into the microscopic, absolute chaos of the kinetic theory of gases. Just take a look at this massive, incredibly sturdy stainless steel tank. We're talking 18 cubic meters of solid metal. It was filled up with high-temperature steam, completely sealed off, and then rapidly cooled down with a fire hose. And the result? This completely dramatic, catastrophic destruction in under a minute. I mean, it literally looks like some invisible giant from a sci-fi movie just stepped right on it. And honestly, this brilliantly sets up our core mystery for today. How exactly can an invisible gas exert enough force to crush solid steel like a discarded soda can? To the naked eye, a gas seems like nothing at all. It's just air, right? But thermodynamics tells us a totally different story. So to understand how this happens, we're going to use a sort of macro, micro, macro zoom arc. We'll start our system initialization with the macroscopic illusion, then zoom into the microscopic dota, check out collisions and speed distributions, scale back out to energy and degrees of freedom, and finally hit the mechanics of adiabatic expansion. All right, starting off with part one, the macroscopic illusion, the rules of the grid. Down here in the human scale world, a gas basically just looks like a uniform volume filling up a container. We use broad variables, volume, pressure, temperature, to describe what it's doing. But to really understand the rules of the grid, we first have to know how to count what's actually inside. Enter Avogadro's number. When we slant our thinking toward atoms and molecules, it makes perfect sense to measure our sample sizes in moles. Doing this guarantees we're comparing samples with the exact same number of particles. 1 mole of literally any substance contains exactly 6.02 times 10 to the 23rd power elementary units. That is an unimaginably large number, but it gives us the perfect bridge between the mass of a sample and the sheer, mind-boggling quantity of individual molecules bouncing around inside it. And that brings us to the macroscopic baseline you're probably pretty familiar with, the ideal gas law, PV equals nRT. It dictates that absolute pressure, volume, and temperature in kelvins are all inextricably linked, scaled by N, the number of moles, and R, the universal gas constant. Now, when a gas is at a low enough density, its molecules are spread far enough apart that they basically don't interact with one another. This lets us treat it as an ideal gas, which is great because it gives us a perfectly clean mathematical baseline to predict its macroscopic behavior. Moving on to part two, zooming into the microscopic, translating the data. So, leaving the world of broad measurements behind, we're entering a realm of constant, frantic motion. The crucial point here is translating between these two worlds. What we actually feel is human-scale temperature. That's really just the average translational kinetic energy of these microscopic particles. And what we measure as pressure? That is literally just billions of tiny, violent collisions against a container wall. When a molecule bounces off a wall, it transfers momentum. The collective force of all those tiny, relentless impacts over an area is exactly what we call pressure. To give you an idea of the microscopic chaos taking place right in front of your face, let's talk about the speed of these particles. The root mean square speed of hydrogen molecules at regular room temperature is an astonishing 1920 meters per second. Think about that. That is literally faster than a speeding bullet. The microscopic world isn't gently drifting around, it's an environment of extreme, hyper-fast ballistics. In fact, this speed actually sets the absolute speed limit for how fast sound can travel through that gas, simply because sound waves are passed along entirely by these particle collisions. No way around it. All right, part three, collisions and speed distributions, navigating the neon city. Let's try to isolate just one of these incredibly fast molecules as it attempts to navigate the system. As you can guess, it's not a clear path. The environment is incredibly dense and packed with obstacles. We use a parameter called the mean free path to describe this. Think of it like a molecule trying to sprint through a very crowded, neon-lit city. First, it travels in a straight line. Then bam, it suddenly collides elastically with another molecule. It abruptly changes direction and speed, and the whole cycle repeats. The mean free path is just the average distance it actually manages to travel between these collisions. To put that into perspective, in oxygen at room temperature, a molecule has less than a nanosecond between impacts. That means it is suffering roughly 4 billion collisions every single second. Now, obviously not all molecules are moving at the exact same speed. This reveals a sort of cosmic speed distribution mapped out by James Clerk Maxwell way back in 1852. While the highest number of molecules huddle around the most probable speed, you'll notice the average and root mean square speeds are pulled higher. Why is that? Well, it's because of a few extreme rule breakers hanging out in the high-speed tail of the distribution. And these ultra-fast outliers are absolutely crucial. Without them, we wouldn't have the high-energy particles necessary for things like water to evaporate, which means no rain and no sunshine. Pretty wild, right?
Okay, let's look at part 4, energy and degrees of freedom, scaling back out.
So we know temperature relates directly to kinetic energy, but how much energy can a gas actually hold? What's really fascinating here is how the literal physical shape of a molecule dictates its energy capacity. According to the equipartition of energy theorem, every independent way a molecule can move, which we call a degree of freedom, stores a specific slice of energy. A simple monoatomic gas, like helium for example, is basically just a single dot. It can only move in 3 translational directions: up, down, left, right, forward, back. But a diatomic gas like oxygen is shaped more like a dumbbell. Not only can it move in those 3 directions, but it can also spin on 2 axes. Those extra 2 rotational degrees of freedom allow oxygen to store significantly more internal energy, giving it a higher molar specific heat. It's like it has extra pockets to hide energy in. Which brings us to part 5, mechanics of adiabatic expansion, the grand finale. Let's zoom entirely back out to the macroscopic world. Imagine our gas is expanding rapidly. Maybe it's pushing a piston outward. Because this process happens so incredibly fast, or maybe it's just really well insulated, absolutely no heat is transferred in or out of the system, so Q equals 0. But the gas is still pushing against its environment, right? It is performing macroscopic work. And according to the first law of thermodynamics, if it does work without absorbing any heat, that energy has to come from somewhere. As a result, it forces the internal energy of the gas to completely plummet. And this leaves us with a pretty profound realization about energy conservation. The microscopic kinetic energy of those billions of particles was literally sacrificed to do macroscopic work. Because their kinetic energy dropped, their speed dropped, and therefore the macroscopic temperature dropped dramatically. And this perfectly explains the terrifying power we saw in that crushed steel tank at the very beginning. When the internal mechanics of a gas rapidly shift, whether it's cooling, condensing, or expanding, the macroscopic pressure adjusts with immense, literal crushing force. So the next time you casually wave your hand through the empty air, ask yourself, just how much invisible power are you really pushing against?